Norberto. Perdón. Ya está. Nos visita hoy Norberto Nigro. Ya nos ha visitado por suerte varias veces. No sé si lo han escuchado anteriormente. Esta vez está dentro del plan del programa Severo Ochoa. Va a estar 2 meses acá. Norberto es profesor de la Universidad Nacional del Litoral en Santa Fe, Argentina. Y es investigador principal del CONICET. El CONICET es el principal órgano de investigación de Argentina y dirige en el CIMEC, en Santa Fe, Argentina, un grupo de investigación en ingeniería mecánica. Se dedica a cosas como motores de combustión interna y cosas bastante difíciles de entender. Pero tenemos varios trabajos en conjunto. Estamos en este momento trabajando por lo menos en 3 cosas distintas y hoy va a hablar sobre una de estas. Así que lo dejamos para escucharlo.
Well, thank you very much, Sergio, for the introduction. For me, it's a pleasure to be here in Sydney. I have come here several times, like Sergio said, and since 2008, almost once each 2 years. So I have involved in different projects, and now we are going to present this methodology called pseudo-DNS. It's a pseudo-DNS, direct numerical simulation, and it's called to be a precise and efficient alternative to solve field mechanics problems, especially in turbulent regime. And in this occasion, I want to show you an updated revision of this work. First of all, we have to be some historical projects. 2 or 3 years ago, I went here at Sydney and worked with Sergio in trying to apply this methodology to the scalar transport problems, not only on fluid mechanics. And I want to start showing you some preliminary results about using this methodology to scalar transport problems. The main focus is to avoid spatially unstable solutions, because you have to know that, or you know that the scalar transport problem, especially in aviation dominated flow, needs stabilization. So this is one of the main features of the pseudo-DNS. Avoid completely the use of stabilization. It's not necessary to use this. So the next is physical reasons, because, for example, when you have a high gradient flows close to the boundaries or whatever, especially in stable flows, it's very useful for such a situation. Also for other physical reason, that is when you have a wide range of scales, temporal and spatial scales, like in a turbulence, you have to solve with another methodology. I want to show you the comparison with runs, with ADS, with another kind of modeling techniques. And finally, in heterogeneous flow, that I'm not to introduce or include in this presentation because I'm not involved in such an application. Jimenez is one of the ones with Sergio and Eugenio are involved in this very challenging, very difficult problem. So what is the theory behind this novel methodology? I want to show you some briefly aspect about the theory, how to overcome the issues that the DNS has, because if you want to improve your accuracy, you have to move to DNS, but DNS is very difficult problem because you need a very fine meshes. So finally, what's the development progress status of the technology, the current possibilities, next challenges about the usage. So the PDNS is more or less a resume or summary in trying to separate the solution in two parts. One in solving the coarse mesh and the other solving in the fine mesh. Here you have the coarse mesh and you have the fine mesh. So how can, if you solve in DNS, you have to solve all the problems in this kind of mesh, but it's very, very expensive to do that. So we have to move or to combine the usage of these two meshes. In the fine mesh, the solution is obtained by DNS, trying to resolve all the scales that are present in the fluid. But in this case, trying to avoid the expensive situation of DNS, we solve this problem in an offline simulations using the concept of the representative volume element, or RVE, that is very common in multi-scale problems, and try to move these solutions or some sort of average of the solution to the coarse mesh. And the exchange data is stored in dimensionless way in order to not to reproduce the infinite kind of problem that you have. Also, with dimensionless parameter, you can move to solve only a finite set of different problems. So with this solution in the RVE, in different situations for different dimensionless parameter, you build a sort of database for all the possible cases. And in this case, it's possible to have a very representing universe of the different situations, especially in terms of these dimensionless indicators. And for the RV database, we construct a synthetic model to emulate the fine scale simulations. Well, in order to know or to have an idea about how to apply this for a simple problem like a scalar problem, we start with convection diffusion problems. It's very familiar with all of you. And in this case, we, for brevity reason and for clarity, I prefer to start in 1D situations. And the splitting of the problem is inherited by the solution. The solution also is split in two parts, the coarse and fine mesh. And this is a look of how a solution looks like in a mesh. Yeah, the red one is the coarse solution, the green is the fine solution, that we have to integrate this contribution in each of these elements or cells and try to upscale this contribution in the coarse mesh. So for this kind of problem, that is very in particular, it's very different to the fluid mechanics problems, because in the fluid mechanics problem you have the nonlinear terms that produce the chaotic motion, the chaotic representation of the solution, but here the velocity is imposed, so you don't have non-linearity. A linear problem, so this kind of features produce a different approach to this problem. So we impose some restrictions on the fine scale solution, for example, that the solution at the end of the I make a problem because no, forget sorry because the because the well, I said that it's the different approach because the nonlinearity is not appearing in this problem, and here we have the splitting of the variables, and we solve the two problems, one on the coarse mesh and one on the fine mesh, with the different weight functions like this. And where after weighting and integrating by parts, we have to put that representation of the solution, split representation into the formulation. You have different terms. This is the problem on the coarse mesh. This is the problem on the fine mesh. And it's not in pantalla completa. Okay. And finally, after some algebra, very simple algebra, you identify that with this restriction, disappear some contributions of this gradient or diffusive terms, and also and only remains these terms that should be computed. So you have to compute the integral of the fine solution in the RVE in the fine mesh and upscale to the coarse mesh. So the coarse mesh equation is like this. If you try to solve the problems in the RVE, you can get the fine solution, integrate, and upscale in the coarse mesh. And how we solve the problem in the fine mesh? Well, we try to put these coarse mesh problems. That is, for example, here you have the coarse solution, you have the fine solution, and you have to convert this problem in a dimensionless problem here in the RV, where you have to maintain or to keep the same no sé por qué se salió de la pantalla completa de vuelta. You have to you have to keep the same dimensionless parameter. In this case, advection diffusion, you have to maintain the same Peclet. So you solve in the fine mesh two problems: one for a fixed mean value and one for a fixed slope or a fixed gradient. So two canonical problems serve for trying to integrate the integral of the fine mesh solution, and this is the contribution in the RV, and you have to identify this. This is a sort of database. This is our database in terms of a very simple functioning, that is the bridge between the RVE and the course. So you can identify this term, that is the term that the coarse mesh needs. So, but you have to convert, because this solution is dimensionless. You have to pass to the dimension world, and so this is the conversion factors for this very simple problem. And this is a summary of the problem. You have different elements in the coarse mesh. For each element, you identify the Peclet, or in this case, the Peclet, and you solve the same problem for each coarse mesh cell in the RV, and you, in this case, you use the database that is previously constructed or previously built with a swept in the Peclet numbers in this case. And also we extend this for the reaction, convection and diffusion in steady states. Here appears in other terms when you make an algebra with the splitting of the node, that is not only the zero moment of the fine scale solution, also the first moment of the fine scale solution. So you have to construct two variables, tau and tau x, with two canonical charging states. So this is some summary about how the technique works. You have to solve this problem. You split in two problems, one for a constant mean value, one for a constant gradient value. G0, G1 means these two charging conditions, and you maintain or keep the Peclet number, the reaction number, And with this information, you construct the integral of the tau and the integral of the tau x, and upscale this information to the coarse mesh solution. Here there are two papers that we publish in this with this contribution. This is more or less the same, so I prefer to go further. This is some solution when this is very simple problem, because in 1D all the world knows that it's very easy to get the exact solution. This is the magic function in finite elements or bubbles or whatever. And here some results that show or demonstrate the ability of the method. This is the convergence of the method especially in not only in the fine. If you refine the fine mesh of if you refine the coarse mesh, you reach H square conversion rate. This is another or an extension to unsteady problems. We solve the unsteady problems also. In this case, 1D, with a very interesting conversion rate. It's like 3 orders of magnitude, order H cube, for different problems. Here, for example, C is the reaction number, so DC is a reaction number of 100, and here is a reaction number, Peclet number of also 100. Also for more reaction number is 1000 and the same Peclet. And here is some solution, how looks the solution in unsteady problems. For example, this is the initial solution, the magenta is the analytical solution, and this is our solution in unsteady problems. Here you have to make some particular sort of implementation, because you have to, well, our idea is to solve the time dependent problem like a pseudo-stationary problem, a pseudo-steady problem, with some sort of body forces enhanced with projections on space, a greater dimension space. So it's a technique that enough particular. We extend to the problems. This is in this case it is in progress, because we have some sort of difficulties in identifying which are the better or the best problem to be solved in the RBE. In the RBE, you have to define the problem. For example, in the next slides, I will present fluid flow problems in turbulence, and you use normally periodic boundary condition. But in this kind of problem, periodic boundary condition, at least this was not my choice. I don't want to say that it's not possible. Probably yes, but I prefer to use fixed Dirichlet boundary condition in the RBE, and I put this when you move to the 2D problems, you have to impose boundary conditions. For example, if it is the RBE problem, you have to impose the Dirichlet boundary condition in all the edges of this element, and it's not so easy to reproduce the exact solution. It's very difficult. And now we are trying to do with some neural networks environment in order to make some training to different kind of situations. So it's in progress, this kind, but we have preliminary some good results for this particular problem. It's not a problem with a very high Peclet number. If we have some reaction number, this is the way in which it looks when you have a reaction, and this is our solution that is not so bad, but this is in progress now, right? The next is I'm going to move to the theory of in fluid mechanics when you try to solve the turbulence. So first of all, I want to define some notation. For example, when you when you try to solve the instantaneous field, this is the way in which look. If you make a spatial average, you have a hat here, and you a temporal wedge and hat is a temporal and spatial average. I try to condense all the notation in this way. It's probably it's not the unique way, but it's my way. And this is dimension with dimensions, and this is dimensionless. So when dimensionless, you have a tilde. So if you see a tilde is dimensionless, if you hat is spatial, if you wedge is temporal average. First we try to solve the problems in fluid mechanics, and first of all I have to separate in two words. The first word is the internal flow. It's different to treat internal flow than boundary wall flows. When the flow is close to the boundary or close to the wall, you have to solve this kind of problem in a different way. So first of all, I want to show you how to treat internal cells. In internal cells, because the splitting is different, the splitting of the variables. In internal cells, we prove with this kind of solution, a coarse mean value solutions, and the rest in the RBE. The rest, I mean, for example, the fine solution, and also the contribution of a gradient, because this is a bridge between the coarse and the fine mesh, the gradient. The gradient is the input to the RBE problem to identify which condition is going to be in order to detect which kind of turbulence or which amount of turbulence is happening. You split all the velocity and the pressure. With the pressure, I have no much more to say, because it's probably the problems that we solve are not so dominating with the pressure. And when you replace this in the Navier-Stokes equation, the equation looks like here. And this is in the Eulerian framework, and this is in Lagrangian framework, where we use the U value. U value is the total velocity. So I have a problem like, there, because I don't know which is the whole problem in the coarse mesh. First, previous to solve the fine mesh, so we prefer to move to the ALE formulation, where instead of U we use UC. So this is an extra term that appear in order when you move from U to UC. So here you have this the stress tensor in the coarse mesh. This is the stress tensor in the fine mesh, and also we have to impose the incompressibility. And when you move in these equations in a residual form, in order to do the weighted residual formulation, this is how the residual looks in ALE, where this is the fine scale contribution, and this is in a Eulerian formulation. The different here is in this part. In this part. So when we put in the weighted residual formulation, we have the normal wave function in finite elements, or if you if you use another technique, is equivalent. So this is all that I have to compute in RB for the fine scale in an offline way for constructing a database. This is more or less, this is a summary, and we solve two kinds of problems. One in the coarse mesh and one for the RBE. So I have to let you know how to solve such two problems. we implement, or we think, not implement, we think the problem in these two numerical methods, FEM and finite volumes, but we implement, well, one implements this in finite volume because we use OpenFOAM that is built in finite volume. So for us, it was very useful to do that. So there is some constraint to impose the incompressibility that I say for the two problems, the coarse problem and the fine problem. And also for the fine scale fields, we have to impose these conditions that looks like some sort of weak periodicity condition, and we move to strong periodicity condition because it's more easy to implement. This condition is not assumed in the integral of the boundary, also not by node, no? So it's strong. In this sense, it's something different. When you put this constraint in the formulation, and after some simple, very simple algebra, finally you reach these two terms that you have to include in the formulation, that you have to solve in the RV and upscale to the coarse mesh, coarse solution. This is for FEM, and this is for finite volume. Looks like very, very similar. And we assume that this term is approximately neglected because experimentally we see that the contribution is very, very neglectable, and we neglect for our solution. But this is one thing that we have to prove, no, Juan? Okay. So this is how the coarse mesh, so the coarse problem looks. You have to, at this moment, to solve for a stress tensor, inertial stress tensor that is defined in this way. This is the continuous version, and this is the RV version. The RV is almost the same, is approximately equal because you have to solve in a RV that represents some sort of the influence zone in each coarse mesh set. So the problem in the RV is like this. You have to solve in a standard cube of H1 as the size of each side, and with a fixed viscosity, we fix the size. So you identify some sort of number, dimensionless number, that is proportional to the gradient of the flow. So the turbulence is promoted by its gradient. And when you construct this, G is a tensor, no? ID should be a tensor also. But if you do some sort of rotations, you can put the tensor in a pure shear stress condition. And this is the representation of this ID indicator when only two numbers remains in the problem. We call ID1 and ID2, and we apply periodic boundary condition as I said before, and this G that comes from the coarse mesh is some sort of the source for the RV, the same for the pressure gradient. If we introduce a pressure gradient, that in this implementation we don't have pressure gradient included. So from the coarse mesh, you take the G, the gradient, the velocity gradient, in dimensionless way. First, we symmetricize in order to disappear the pure translational and rotation movements. We only remains the deformation. And as I said before, we have some rotations in order to convert this full tensor in a very particular tensor that depends on of two parameters. So then we try to solve in the RV. This is the problem to solve in the RV, where finally we applied a pressure gradient null, as I said. So the pressure is periodic, and the mean value is null. And this is the value for the RV. So when you solve this problem, you get a RV solution and RV velocity UR, and with this UR you take the fine contribution with this such subtraction, and with this UF you construct your tensor that should be upscaled in the course lecture. So as a summary, two input data, ID1, ID2, constructed by the G, or the gradient of the velocity, and 6 output data, the inertial stress tensor in temporal and spatial average. So we finally construct the database in a dimensionless way. And here is a representation of different situation for different ID1, for different ID2. We swept in these two different values. And we construct this tau over G. This is an old version, because in this version we use some Boussinesque representation of the turbulence, like modified viscosity. But now we changed our mind and moved for tensor, where we can also include the anisotropic behavior. So this is some sort of the result. With this data we construct some database or neural network or whatever. And this is well, some demonstration of the convergence of the problem in the RV. This is how looks the components of the Reynolds stress tensor, the inertial stress tensor, and this is the summary. We have to show that the problem in the coarse mesh is gets from the database, get the information needed according to the gradient, velocity gradient, to include the contributions of the fine scale that, as we said, we solved previously offline, like a reduced order modeling or family. First results, one topic that is very important is when we construct the database, we assume the equilibrium. We assume that the problem reach the equilibrium. So if you look this, we assume the equilibrium. But in the computation of the flow, this equilibrium is not reached. May be not reached. So you have to take into account this different situation with and for that, in order not to include the time, because for the time was a very difficult problem, we use some sort of memory factor. So we combine the previous solution and the current equilibrium solution in some way with some factor m that is compute in this way. Is some sort of the time relaxation and exponential decay with a certain time relaxation that should be also automatically obtained by the velocity gradient and in the current state, the velocity gradient in the old state, and a factor that was tuned, was trained in order to get a good prediction of this tau or relaxation time. But one thing that is very important is that this G is not the velocity gradient in the previous time step, is the velocity gradient that making inverse engineering you reach when you take the tensor in the previous time step. So because this is the real value. So this time relaxation was calibrated with different simulation, and also with the examples that I am going to show in the next. For example, this is the decaying turbulence problem that is very well-known benchmark that serves also for getting a calibration for this time relaxation. And this is, for example, how the decaying turbulence looks in our simulation. For example, the reference DNS is the black one curve, and here we have the kinetic energy respect to the original, the initial kinetic energy, how it decays in time for different meshes. Meshes with 4 cube, 8 cube, 16 cube, and 32 cube these points. And this is how it looks for different levels of turbulence, initial turbulence, for pseudo-DNS in red and for less in blue. Even though with the finest mesh that we use, that is 32 cube, both look similar, it's very important to note the difference when you move to coarse mesh. The convergence in mesh is more faster with the pseudo-DNS than with the less solution. That is very remarkable in this problem. So also the less looks very inaccurate for very coarse mesh. No, that is very known result. This is another problem. This is a mixing layer problem where you have two flows with a shear between them, one with U1 velocity and the other with a U2 velocity. This is a paper where we take the example with different boundary conditions that are very common, traditional. We analyze the problem in 3 different meshes. This is 128 times 30 cells with this time step. This is a double in the 2 directions, and yes, double of the double. So we try to solve it, and this is how they looks in the coarse mesh. The coarse mesh is difficult to get the real representation of the flow because the coarse mesh is really coarse. So we want to make a very coarse mesh, as coarse as we can. But here also we use the previous version that is effective viscosity. This is one of the our first examples that we try to represent with the technology. But so we here we mentioned that this kind of turbulence identification factor, like the modifier of the effective viscosity, is now deprecated. And well, this looks very different for one for another. And this is one thing that is very important, that the refinement move the limits of what you solve, of what you represent with the coarse mesh versus what you represent from the fine mesh. And even though the patterns looks very different, here there are 2 results that are very important. This is the velocity, the stringwise beam velocity, that in dot squares, in black squares, you have the the reference, and in red the pDNS results. And you have with this with a very coarse mesh at 4 different stations, no? X point dot 4.45.5. This is represented by this, but you have to know that the problem for the formulation is like the theory said, is self-similarity. Self-similarity looks like it said that for the 3 position you have the more or less the same. That almost is reached here, and when you improve the mesh, you can get more precise results. That is very interesting results for us. This was our first serious problems solved. Another is the Taylor-Green problem. The Taylor-Green problem, here we measure with less about the capability to solve this problem where with different meshes. For example, even though the DNS solution is 256 cube grids, that is very, very unthinkable for us to do that at present. pDNS unless was solved with a very coarse, fine, medium and fine mesh in order to know how reproduce this very interesting problem that is defined as 2 initial vortices decaying in time, interacting between them, with the velocity at time equal 0, at time equal 20 seconds in 20 dimensional unit time. Here is how the kinetic energy and the dissipation rate looks for the different method, red pDNS, blue less, and for different meshes. No, the meshes that is very fine, more finer, are more precise with the reference that is in black, and also for the less. And again, you have to know that some coarse mesh solution in less are much more far away from the reference, and for pDNS is a little bit better. Another problem is backward-facing step that we solve in 3D problems, in a 3D wave. And in this problem, it's important to identify the reattachment length of the flow. And this is our experimental data was taken from this paper. It's a 3D turbulent flow. The reference, DNS reference, used 6 million cells. We use 140,000 cells, also with less and pDNS. We use some sort of boundary condition for the inlet for promoting the turbulence using some sort of digital filter method. And we predict the mean quantities using core mesh. And this how the result looks. In red pDNS, in black the reference, in blue the LDS. Here you have the difference. You have to know the difference that here disappear, the difference between pDNS and less, but LDS. But at this moment or at these stations, the problem is very important. Here you have the cause, the reason of the different reattachment length. So here you have the CF, or mean friction coefficient, for the reference in black, again, the pDNS in red and LES in blue. When we have a better representation in the first part, and also here in the pressure coefficient, but in the friction we have some difference. This approach is older, so we have an improvement now that probably is responsible for such a difference. So we have the expectation that the result would be better, would be improved. So, well, this is another profiles for component of Reynolds stress tensor, U prime square, U prime B prime, W prime square. So finally, in this part, we solve the square cylinder, and we follow the work of Terraza people, Asensio Oliva, these guys that are very, very important group in experimental in DNS, computational fluid mechanics. This example was chosen because the square cylinder promotes the separation. So at that moment we didn't have how to solve wall-bounded problems like now. So we try to choose problems that the boundary layers were not important. No? This is one of them. So the focus was only in the bulk of the turbulence in the bulk with the different meshes, and compare with the DNS, 300 million, 2 million. No, it is very, very different. But the results, when this is boundary conditions, how the scheme is set up, and this is how the comparison looks. This part, the comparison is not so different between PDNS and less, but here we have different contribution of the stress tensor. For example, U prime square or U prime B prime. The red one, the PDNS, follow the solution in a better way here, for example, and here, for example. So this is a resume or a summary of the different methodologies, DNS with Strouhal number, with CD are some root square average, CL, the same for CL, and this is important. No? The length of the reattachment in the top, in the sailing of the square, that we reach more or less, or more close value to the DNS than LES. So we predict some sort of good results. And this finally, I want to show how we solve the problems in the wall-bounded problems, in the flows close to the wall. Flows close to the wall are not so free like in the bulk, because in the bulk you assume some turbulence, but on the walls or close to the walls, the flow is more constrained. So we adopt this solution for the RV. We make an RV that is double in height than in the base, and we impose two velocities, and then we measure only the lower part, the half lower, in order to identify the properties. But this kind of RV doesn't work so well for the problems that have a boundary layer development. So we move to this kind of approach when we start with an RV with some dimension in base, some dimension in height, and we impose one velocity here, an initial condition that is the piston flow, that is the same in all the height, and we free the simulation, and at each time step and at each height, we measure some quantities that we consider that are important to be upscaled to the coarse mesh problem. So with this simulation, we have to move with another splitting, like I said before. The splitting now is this. We introduce this guy that is an enrichment velocity, because close to the wall, the velocity, the profile of the velocity is curve. It's not linear. It's very important, the contribution of this curvature, especially for example, if you think about Nicuratse profiles or Blasius profile or slit profiles that use 1.7 or 1.5 or 1.6 profiles for the velocity. No, the velocity is u over u infinite is proportional delta a la 1 sobre n en 5, 6, 7, 5, 6, 7. So this kind of profile is not possible with a linear assumption for the RV. So we moved for this solution. But this splitting obviously introduce some modifications in the formulation. Not only here, not only this guy. You have 3 more. Yeah, one is the viscose. Because now you have a contribution of it's not possible to assume the same as in internal flow when you put the gradient of the U fine is 0 in average. Now it's not true with this one. So this is the contribution of the viscose part. Also the interaction between enrichment and the fine solution, the enrichment itself and the enrichment with the fine solution. So you have these contributions. Up to now, we are neglecting this, Sergio, but in the future we are trying to include, because it's probably it's not influencing enough for the solution, but it's better to have also included in there. So the enriched solution looks like here. We impose only the enrichment in the tangential component of the velocity. In local reference frame, you put this guy. Here is a special tensor. This, and in the T mu or the viscose part also, we only assume the variation of u in the normal direction of the wall. So this is how these 2 tensor looks. And also, because we use in finite volumes, the divergence of the tensor is by the divergence theorem is like this. So you have to, this is approximately sum over phases, the T phase and phase and the gamma phase, the area of the surface, the area of the phase, the normal of the phase, and the tensor applied on each phase. So at the bottom, you have here a TF that is not known. So it's very important. This is one of the most important, because it's the force that decrease the velocity. No? So you have to identify also in the RV, which is this guy, that this computation, this vector. This is a vector. And for the enriched fine cross tensor solution, well, we have to compute this, but I said this is not. So we have to, as we said, in the RVE, we have to solve with the 2 free parameters. One is some sort of dimensionless time, and the other is some sort of height from solid wall. So we start simulation at each time step, and at each height we make first the instability index and dimensionless, some sort of the time dimensionless. This strategy was changed now, I was to tell you now. And this is the 4 tensors, or the 3 tensors, the vector, and I forgot to put the other tensor, the interaction between fine and enriched, that have to be computed. This is a more updated version. We have 2 numbers, ID1 and ID infinite. The ID infinite is this computation include the viscosity that is fixed in the RV, the U, that is the precursor velocity, the trigger velocity, that is also fixed, and the H that is variable. So as we go up in the theta direction, in the normal direction, the H change and the ID infinite change. And when the solution evolve in time, the UX, this is the average in space for each H, see, up to each H, the average of the velocity is changing also, as we are showing next. And with these two, you compute the database for the wall-bounded problems and then the different tensors. This is how it looks. For example, this is a time-developed layer RV. You, for example, you take different H to compute, and you evolve from the beginning, and the delta is the thickness, the momentum thickness of the boundary layer, change in time. This is evolution in time. This is evolution in delta. With this delta, the UX, the average at different height change. With these changes, change the ID1, and also you have different ID1 for different ID infinite, and you can reproduce or complete the whole boundary layer. This is how it looks. First, you have a profile similar to this. It's close to this guy with 1.7, for example. And the average is close to U because it's almost a piston flow velocity. But as the time increase, the time evolve, the profile is getting in this way. So the average is reducing. So the ID1 decays, yeah? Or increasing this way, and the time increasing this way. So as the time is longer, the ID is lower. So this is just, and resembles some sort of the delta that is the boundary thickness. This is how it looks, one of the components of the tensor in the database for different U infinite or ID infinite and ID1. The blue is the points that we really simulate, and the red are points that are extrapolated. Because we need a lot of time for getting, and we try to convince you to join us in order to get those points. So the green are the points that we have. The blue are ISO lines for different values, and this is what we extrapolate. Also, this is the same picture, but in snapshots. And results, well, we prove this in laminar boundary layer over a flat plates with a very typical problem with a reference solution like Blasius solution. And we found this behavior. No? This is how the profile looks for different RVE that are placed here according to the condition of the ID1, ID infinite of the flow. And it's very important that with this coarse mesh, the boundary layer is in the first cell. No? So thanks to the new splitting that includes the enrichment, it's possible to get good solutions because this curvature is only responsible for this red enrichment solution. This is how the delta evolution for us compares with the Blasius solution, and this is how the friction coefficient compared with the Blasius. So this is the same for turbulent with the reference of Schlichting, and the same. This is how move from laminar to turbulent. This is the black one is laminar solution. The dot one is turbulent, and we promote this change using some criteria, personal criteria. It's between brackets. I don't know. We have to improve in this way, trying to get which is the Reynolds number for delta critic for the this transition. We promote the transition up to now. And finally, we solve the NACA 12 simulation, validation with the NASA results. This is the mesh of NASA. It's a very, very fine mesh. We use this mesh. We use a coarse mesh, coarser mesh. For example, here you have the mesh of NASA, 1.79 microns of height, and we have here our mesh. Our mesh is this one. Yeah, it's 5 millimeters. So the problem, the NASA problem was solved using spiral almaras. That is one of the famous method for such a problem, because it's very, very good for this kind of problem. You have the three meshes: the NASA mesh, our fine mesh, and our coarse mesh. Where we want to show, for example, this is in the profile. I put some stations in order to show how is the NASA results in this station. The profiles in this station looks like here, like this. Sorry, this is the velocity in the height for different the 13 different stations that I put. And this is, if you move this information to our ID1, ID infinite for different heights and for different stations, the cloud points lies here, like in this way. For what is important is, because if you have a database built with information that only have up to 200,000, the limit of your coarse mesh should be 20 millimeters. You don't have to do simulations with mesh coarser than 20 millimeters, because you lies outside of the database and your results makes in a danger region. So this is some sort of previous indication about how coarse would be your mesh in order to get solution that use information, good information from the database, and not garbage. You know? And for example, for the NASA value, you have this behavior for the ID1 and ID infinite. And normally you need that ID infinite should be greater than ID1, but in this case, because these curves are built using the very, very far value of the profile in each station, this value, these curves cross between them, but this is spurious, no? Because the condition is not good enough. You have to select the farthest velocity, else the maximum velocity. Well, and finally, this is I think the best results, because you have here the fine mesh, the very, very fine NASA mesh. No, sorry. This is the NASA mesh. This is the result of the NASA mesh. This is the result of pseudo-DNS with our fine mesh, and this is spiral almaras with the same fine mesh. That looks very similar, yeah, and similar with the reference. So with the fine mesh, both pseudo-DNS and spiral almaras behaves well enough. But and this is the friction coefficient in the intrados, the extrados. But I want to show this, because if you move to the coarse mesh, the reference says always, no? Because it's always in the finest mesh. But in our coarse mesh, our results are this. No, there is no separation here. This condition of the flow is not is without separation. but spiral armors separate, so with the coarse mesh. So we try to convince you that our simulation in this, our technology, pDNS, in this case for NACA 12 with spiral armors are good enough. This is why, this is the reason for the evidence of the separation. You have the friction coefficient negative, so it's not possible. This is how the pressure coefficient looks like with the finer mesh. This the CF for the finer mesh. Always reference is black, pDNS is red, and spiral armors is blue in this case. And this is for the coarse mesh. So this is numbers that allows to show that pDNS at 0 and 10 degrees for CD and CL, drag and lift, are very similar to the reference. For example, the reference for 10 degrees is .011, our is .012, and this is 107, 107. That is very, very nice. That's very, very happy. What is done? pDNS has shown to be able to solve academic problems with a very high level of accuracy, approximately DNS, or trying to approximate DNS, and efficiently, similar to RANS, because our coarse mesh may be the RANS mesh. It's numerically stable for any coarse mesh use. In terms of accuracy, it's much more convenient than any RANS for industrial type of mesh. In terms of efficiency, it's much more convenient than any less, also for meshes where less is not possible to be used. And our extended database for internal and also for one was developed, and database are able to solve any problem, only adapt coarse mesh to its limits. Is our recommendation. And the next step, solve more challenge problems, social and industrial applications, not only for marketing, also for detecting hidden drawbacks and for improving some estimations, and convince the public the convenience of using this methodology instead of using RANS or less. And this is some of the publication that we had. This is our team, Sergio and Eugenio, the creators of this idea, and Juan, this is a worker. Thank you, Juan, a lot. Axel, that is a very, very good guy in the sense of theoretical and fluid mechanics skills is very, very important. Francisco Sibor is our new fellow. Sorry. Reinald, that always is important for discussions, and Pavel, that at the beginning worked with us and helped us a lot. And finally, I would thank you for Severo Ochoa program for Center of Excellence in Research and Development, because it's the motive of being here today, and always Sergio and Eugenio, as always, and Sidney and his people, because here I feel very comfortable. I feel very, very happy to be here. Obviously, in my country, CIMEC, CONICET, and Universidad Nacional del Litoral, that are my sponsors. So thank you very much for your attention. Sorry for the time. I don't know.
Un poquito.
Un poquito. ¿Cuánto?
Bueno, si hay preguntas, if there is some question, comments, in English or Spanish.
I have many questions, but they are technical. I will not ask them. So I just have a very general one that refers to the last slide, maybe. When you say that you have the cost similar to RANS, but we have an accuracy similar to LES. So the accuracy measured where? In the coarse mesh, or the mesh that you have?
No, probably with the reference, no? With the reference that we have experiments or very fine solution obtained in solution, very meshes. for example, I have a problem, I solve with the finest meshes as I can, or if I have experiments, put the dots of the experiments. I try to do which coarset mesh for PDNS reach the best approximation to the reference, and with that such a mesh, the runs or the panoramas or whatever, or less or yes, does.
You know, my concern is that you know, you cannot have a method with a smaller computed effort than LES. Why? Because if you claim that you have an accuracy similar to LES, is because you have entered the energy cascade. You have entered the inertial range of the global energy cascade. And if you enter that, the big problem is that you have a limitation in the mesh size. So the wave number that you want to capture has to be 1/h, essentially. And if you want to reach a certain wave number, your h has to be such that 1/h is that wave number. You understand what I mean?
Yeah, yeah.
So but this is let's say a showstopper. You cannot go better than that. The other thing is whether with the same cost as an existing LES, you can improve results. This is possible.
You mean energy range?
So if you do LES, you're cutting your calculation somewhere in the inertial range.
Yeah.
Exactly.
If these structures are.
But the cost, when people claim that LES is very costly, is because that wave number that you want to where you want to cut your calculation is such that 1/the mesh size is that wave number, and that mesh size is very small.
Yeah.
So it's something that you cannot get better than that. Another issue is that with the same cost as an existing LES, say, you get a better solution. But what you hardly will get is an improvement in the cost of LES. You understand what I mean? I don't know if if my point is clear or not.
Yeah, but you understand that we solve in the RV, we solve such
but that's why I asked you at the beginning.
The approximation is that you compact or synthesize your information in an integral.
Right. That I understand. So that's why I asked. I started asking whether you measure the accuracy only, let's say, in the finite element solution, or in the finite element solution plus what you would get from the RVE. So I understand that you measure the accuracy in the finite element mesh, on the finite element mesh.
Yeah, the cost mesh. Right. Right.
So
but
that's
using information that comes from the finite.
Yes, of course, that's for sure. Okay. But if you want to be there, your h has to be 1/h has to be there. That dotted line.
Yeah.
You cannot get, let's say, you can escape that condition.
Yeah, but if this, because this is related with the
h minus 1. This is exactly h. I mean,
so
certain number.
If you get to this point, and in the LES mesh, in the subgrid mesh, you have structures that are anisotropic, non-isotropic, no decay. Therefore,
yes, that's what I said. If you are already there, you can increase or decrease the accuracy. That I agree.
Yeah.
So there are better and worse LES models, or not LES models.
Yeah, but we decrease our quality.
Right. It's very simple. If you plot the spectrum, if you plot the energy spectrum that you got, you will see that if it is correct, you will have to have an H that belongs to the inertial range.
But inertial range is
no. Those are the largest scales. The inertial range is the minus 5/3 cascade. That's right.
In the RVE, we are in the Kolmogorov scale.
That's what I was saying. When you claim that the accuracy is whatever, is the accuracy of the coarse mesh or the accuracy of the coarse mesh plus the fine scales.
Yeah. In some sense,
In other
it's
words,
probably both.
If you plot the energy spectrum
Yeah.
of your solution, you can plot the energy spectrum.
No,
of
but
the solution.
no,
What would
but-
you do?
See, yeah, no. In this case, if I'm interested in this plot, I have to try to get the information of the RV in order to get this one.
So it's not the accuracy on the finite element mesh, but on the
Yeah,
finite element
but
plus.
because you are interested in this kind of plot. If I'm interested only in drag, lift, or Struhan, or whatever,
This is
that if you want to plot the energy with the wave number, yes, I have to take, because here the answer, I think that is this one. Sorry, no. Ahí está. This is the answer. This is the problem. But here, for example, this is the core mesh, this is the coarse mesh, this is the core mesh.
Okay, any other question? We thank again Norberto.